Okay, welcome back, Math Nines. This is going to be our next lesson on 4.2 while I just adjust our windows here. This is going to be on linear relations. Recall in the last lesson, we were working with patterns. We were looking at toothpicks, pizza toppings, driving distance, different things that were related in a linear way. And we're going to look at it more in an abstract way with with a little bit new vocab. So let's dive into these linear relations. Okay, so a linear relation is defined as we have constant change in one variable produces, okay, a constant change on the other. You might think as one depends on the other, which is true. Now, are the following relations linear? These are abstract. We have no context here, so let's see what's going on. We look at the left side first, and we see, okay, every time we go, we are increasing by +1. And now we have to check the right side, and this is increasing by 9. This is increasing by +9 as well, and another +9. Since both sides are constant, then yes, this is linear. Okay, everything is constant change on both sides. Let's take a look at the next one. Again, on the 1, 2, 3, 4, we are going up by +1, but on the right side, check this out, we go up by +2. And then in the next step, we go up by +4. Right as soon as the pattern breaks, we know there's a problem. But let's keep going if we see this is going up by +6. So you can see there is a pattern. It's increasing by 2 each time by how much it adds, but it has to be a constant addition, always the same amount. So this is not a linear relation because the right side is not constant. And let's take a look at this one. Looks like we are decreasing by 3 each time. So minus 3. And then on the other side, we're increasing by +10, it looks like. Yeah, so we're increasing by +10 on both sides, or sorry, on the right side, decreasing by -3. Everything's constant and consistent. So yes, we do have a linear relation. Okay, so in graphing data, we always plot what's called the independent variable on the horizontal x-axis. Okay, this is labeled right here for you. Always, that's where we plot the independent variable. We'll talk about which one's which in a second when we have context. And the dependent variable is on the vertical y-axis going up and down. Okay, we can identify which is which by asking which variable depends on the other. So this idea of dependency is super important. Okay, so we're first going to think of it. What if I was graphing distance driven and time? Now, I'm going to say two sentences, and one of them is going to make much more sense than the other. Does the distance driven depend on the amount of time you've been driving? That's sentence number one. Does the distance driven depend on the amount of time you've been driving? Or does the amount of time depend on the distance driven? Does the amount of time depend on the amount of the distance driven? Now, if you think about that, the one that makes a lot more sense is the distance depends on how long you've been driving. Absolutely. So distance, we call this the dependent variable. Okay. And time will be our independent because time does not depend on distance. Independent um, variable. Sorry, got a little frog in my throat there. Okay. Now, again, distance driven depends on the amount of time. So we call that the dependent, and the other variable would be considered the independent. So in that case, time would go down here. Time 99.9% of the time goes on the x-axis with any real world situation. And over here would be distance. Okay. Now, how about diver's depth and water pressure? Does the diver's depth depend on the amount of water pressure, or does the water pressure depend on how deep the diver's diving? And the second sentence makes way more sense. So water pressure this time, okay, is going to be our dependent. It depends on how deep you are. Dependent variable. Okay, so that would go here. So we'll put WP for short. And diver's depth, that's going to be our independent variable. Okay. So that would be here. We could say diver's depth, dd, okay? Because since pressure depends on depth. So we'll write two quick sentences. We'll say since distance depends on time, and this one would be since pressure depends on depth. Okay, so those are our two statements there. And before joining data points on a graph, you got to ask yourself whether it's possible to have decimal or fraction values for the variables. We're going to see two examples of this. We're going to see one where we do connect them and one where we don't. If the data is continuous, right? So we can have decimals and fractions, basically the numbers in between the integers. It's continuous, okay? It has a curvature or it's connected as a straight line or a curved line. Now, if it's discrete, there's going to be gaps in between points or in between lines. That's when it is discrete, okay? And that's usually when you can only have integer values or some decimal values don't exist. Now, we're going to be able to figure that out in a couple examples. In a table of values, we always put the independent on the left, okay? So always our x is on the left and the dependent is always on the right or the y. All right. So let's take a look at this. We're going to create our first little table of values here. Table of values looks like so. X, our independent variable, and our y, our dependent variable on the other side. And we're going to graph this equation that we have right now. So y is equal to 1 minus 2 times x. And now we get to pick our points, which is really nice. We want to pick easy numbers. And so first number I'm going to choose here is 0. I'm going to put in a 0 because now that once I substitute that in, it's going to be 1 minus 2 times 0. Let's do BEDMAS, multiply first. 1 minus 0 equals 1. So that tells me the coordinate. When I put in an x, okay, of 0, I get an output or a y of 1. So you can think of it as 1 depends on the input of 0. The output depends on the input. And so we have our first coordinate. It's going to go right here. Next, let's pick another number. Let's do 1. That's easy to work with. So 1 minus 2 times 1, we get an input of a 1 in for our x. That's going to give me 1 minus 2, which is equal to negative 1. So this time I get a coordinate of, when I put in a 1, I got negative 1. So 1, negative 1 is right here. Again, plotting points, hover around the origin and then use the two numbers to tell you which way to go. So this tells me to go a positive 1 in the x direction and down 1 in the y direction, okay? Let's put in something totally different like negative 2. Let's try that. 1 minus 2 times negative 2. Now I'm going to multiply these two negatives. That's going to give me a positive 4. So I'm going to get a 5 this time. So my coordinate's going to be at negative 2, 5. So I go negative 2 over and positive 5 up, which is right here. You notice my dots are all on a straight line, which is a good thing. This is a linear relation. And maybe I'll just do one more. Let's do negative 1. Okay, so 1 minus 2 times negative 1 is equal to 1 plus 2, because two negatives make a positive. That's going to give me 3. So my final coordinate is going to be negative 1 with an output of 3. So negative 1, 3, which is right. Did I do that? Oh, I miscounted on that other one. That's not 5. See, this is why we do multiple points, because we can spot a mistake. There we go. My coordinate was in the wrong location. And now, does it make sense to join the points? Well, you ask yourself, is there anything in this question, in this equation, saying I'm not allowed to use decimals? And if it's in the general case, or the abstract case of x's and y's, you always connect it with a line. You connect the curve or the straight line with all the points in between, because there's nothing stopping me from putting in decimal values for my x's. I can do that. It's just easier to work with integers. these points are just my template to draw my line, which I'll do so now. So I'm going to try my best to draw this as straight as possible. Always draw your line all the way through, because I could have picked any point along this line. All these little dots I'm drawing indicate that there are infinite little points in between all the decimal values. Okay, so everywhere on this line contains a coordinate that I could have done over here in my table of values. So yes, we will join the points simply, the easiest way to put it, because decimals are valid. Okay, there you go. Valid, I should say, X values, more specifically, because that's our input. Okay, what patterns are in the graph? Is the relation linear? Well, we can see right away. One way to see this relationship, I'll do it in maybe green, is that I can see as X increases by 1, so I'm going up as X goes up and up and up. Okay, we're going up by +1 each time. What's happening to the Y? It looks like it goes down 2, so -2, and then down 2, and then down 2 again. So again, we can just look at this pattern from a graphing point of view that we have my X. So we say as X increases by +1, Y decreases by -2. Okay, there we go. Now let's take a look at our last example here. We have a one-story building. Oh, and I should mention this was continuous because we could join the dots. We're going to see an example now where it's not continuous. One-story building has a 5-meter high for the first floor, and then as they add more floors, it gets to 3 meters. 3 meters per floor, which makes sense. There must be some type of foundation with this building that raises it up a couple extra meters. So we're going to create a quick table of values here. So we have the, I'm going to edit this a little bit because there is a typo here because it's using F and H here as variables, but it also has M listed in meters. So, but I'm going to be using not S and stories. Let's think of this as floors and F. Okay, so we're going to create a quick table of values for that to make that clear. So over here on the left, we have the number of floors because the height of the building depends on the number of floors, and that's going to be denoted with F, as we just mentioned. And then over here, I have, we'll have the building height. And that's denoted by H. Okay. Now, number of floors, if I have, leave yourself a little bit of room here. We're going to be putting in the 0 floor. So I'm going to put, when we have 1 floor, we had 5 meters. And then it says as you go up, you increase by 3. So 2 floors, I'm going to have 8 meters. 3 floors, I'm going to have 11. 4 floors, I'm going to have 14. You get the idea. And so now we can plot this over here. We can plot 1, 5 is right here. Notice this side's going up by 2, so 5's right in between here. And then we're going to go up 2, 8, and then 3, 11, and then 4, 14. And we see again, these are lining up on a nice straight line, so we have a linear relation. Now, do we join the points? Does that make sense? We do not. Don't join points, because it would not make sense, because decimal floors doesn't make sense or is not valid. You would never build a 6.357 floor building. It makes no sense. So this is a case where we would not connect these. This is what we call discrete. Okay, it is not continuous. let's write a quick an equation using what we've learned from the previous unit. So this is going to be review. So we see on the left side, we have to see that we're increasing by 1. So we're going to be able to make a quick equation here. As this increases by 1, we can see that our multiplier was plus 3, plus 3, plus 3. So remember that this is the multiplier. And we go back 1, minus 3, to get our 0 floor, which is considered kind of the foundation. So if we had, there was 2 meters foundations before the first floor was built. Okay, so now we can set up our equation where the total height is equal to our multiplier, which is 3 times the number of floors, F, plus our 0 term. It started with 2 meters off the ground. Okay, that concludes this lesson. So in review, basically, we started to dive into linear relations in the abstract way, in where there's only x's and y's. We learned what independent and dependent variables were and a few examples in context. The difference between continuous and discrete graphs, when decimals are allowed and when they are not allowed. And we graphed a general abstract line where decimals were valid. And then we graphed a relationship between floors and height of a building where we did not connect them because decimals were not valid while creating an equation. All right, we'll see you in the next lesson. Bye for now.